When we got asked to give this presentation, we had around about 1,500 microservices. Since time has gone past, we've now got nearly 1,600. I checked this morning. So yeah, our microservice ecosystem continues to grow. Here's a connected call graph of every one of our services. Each edge represents a service actually calling another service via the network. The number of connections is really large, and it's constantly changing as new features are being developed. Hi, my name is Suhail, and I am joined by Matt. We're both engineers on the at Monzo, and we spend our time working on the underlying platform powering the bank. We think that all of these complexities about scaling our infrastructure and making sure that servers are provisioned and the databases are available should be dealt by a specific team so that engineers who are working on the product can focus on building a great bank and not have to worry about their infrastructure. They can essentially focus. At Monzo, our goal is to make money work for everyone. We deal with the complexity to make money management easy for all of you. For those who haven't heard about Monzo, we are a fully licensed and regulated bank in the UK. We have no physical branches. We've had this API ever since we began. I think it is a legal requirement to have an API which lists all of your branches, and it's been our least changed service over time. You can manage all of your money and finances within the Monzo app. Yesterday, we hit a big milestone of 4 million customers in the UK. That number actually makes us bigger than some banks in the UK that have been here for over 100 years. Banks that I used to walk past when I was a kid that had physical branches. We also have these really nice, really striking hot coral debit cards, which you might have seen around. And I have been told that they do actually glow under UV light, which is really nice and really good when you are in the dark.
Thanks, Suhail. So yeah, 5 years ago, a group of people decided to build a bank from the ground up. There were a lot of reasons for that, but we wanted to build something that was a bit different, help people manage their money easily, simply. But that means you're competing in a space of, honestly, quite a large number of quite big, very well-established banks. And so when we were trying to work out how we would approach that problem, we wanted to build something that was flexible and could let our organization flex and scale as we grew. So the real question is, with that in mind, where do you start? Kind of occasionally suggest this would be the approach. You just open your text editor, I don't know, start with new bank file, and then kind of go from there. But 5 years ago, I didn't know anything about banking. So it's kind of an interesting problem to start from something where you need to work out and understand the domain, and also work out how you're going to provide the technology underneath that. So in that world, we have an interesting kind of pressure, which is time. Getting a banking license takes quite a long time, as you'd expect. It's important that companies that become banks are well-regulated and have the customer's best interest in mind. And there are lots of things that you need to do to make sure that you're looking after people's money. The responsibility you have there is huge. So at this point, you have an interesting dilemma as a product company. You want to build a product that helps people manage their money as quickly as possible. To do that, you need feedback as quickly as possible from customers. But you can't get feedback because you don't have a product that you can give to people, because you can't take and hold deposits until you're a regulated bank. And so in this world, right at the beginning, we weren't even planning on building a prepaid card. We did that a few months later, and that allowed us to partner with another company and go through the kind of product development process. But at the beginning of that, we needed to work out a way to build a technology platform that would be extensible, so we could quickly and easily adapt to the additional systems that we need to plug into. We wanted it to be scalable. Ideally, we wouldn't have to do a large replatforming effort 4 or 5 years in, which is a kind of common approach. And also only a problem that happens if you're successful. You only need to re-architect an entire system if you actually have scale that requires you to re-architect that. We need it to be resilient because we're a banker, and we need it to be secure again, because we're holding people's money. So with those kind of 4 main things in mind, we wanted to work out what are the choices, the technology choices that we would make to kind of drive those things. So we made a few quite early on. For anyone who hasn't heard, we use Go as our primary programming language. And there's lots of reasons for that, but ultimately, as a language goes, it's quite simple. It's statically typed, and it makes it quite easy for us to get people on board. So if you're using a language that not many people know, you have to get people up to speed on how to do that. But honestly, if you're working in a company where you have quite a large framework, you already have that problem. You have to get people to understand how your toolset works and how your framework works and how they can be effective within your organization. Go also has some interesting things, such as a backwards compatibility guarantee. So we've been using Go from the very early versions of Go 1. And every time a new version of Go comes out, it has a guarantee that we can recompile our code, and we basically get all of the improvements. So what that means is the garbage collector, for example, has improved several orders of magnitude over the time that we have had our infrastructure running. And every time we recompile it, test that it still works, and then we just get those benefits for free. The other things that we chose early on were kind of emphasizing distributed technologies. So we didn't want to be in a world where you have kind of one really, really resilient system and then a second backup system and like a big lever that you pull, but you don't pull very often. Because if you don't exercise those kind of failover modes, how can you know that they work reliably? So we wanted to pick distributed technologies from very early on. We used Cassandra as our database, and back in 2015, Kubernetes wasn't really an option, so we actually used Mesos. But then a bit later in 2016, we kind of revised that, looked around, and it was clear that Kubernetes was the emerging market leader. And before we kind of expanded into our current account, we switched over to Kubernetes. And the thing that we were taking from that is providing an abstraction from underlying infrastructure for our engineers who are building banking systems on top of that. Yeah, I think the first version of Kubernetes we ran in production was version 1.2. So for anyone who has used those versions of Kubernetes, that was an interesting time. And there were many benefits to moving to Kubernetes. We actually saved loads of money quite quickly. We had lots of machines that were running like Jenkins worker pools and loads of other things that we couldn't easily run on our Mesos cluster. And by moving to Kubernetes, we could use the spare capacity on the cluster to kind of do all of our build jobs and various other things. So we could more tightly pack our applications, and that saved us a load of money. We shut down loads of other infrastructure. But it wasn't all plain sailing. So one of our values at Monzo is that we're very transparent. We believe that that is the right thing to do. And unfortunately, sometimes that's quite painful. So as an example, in, I think, 2017, we had quite a large outage because of a combination of bugs between Kubernetes, how it interacted with etcd, the backing consistent storage layer, and Linkerd, which we were using at the time, Linkerd version 1, as our service mesh. And due to a combination of different bugs, which honestly quite hard to test, that resulted in a complete platform outage for us. And so those are things that we have to think about as we are developing and introducing new technologies and evolving how our platform works. We have to think about how can we test them, how can we be confident that we're providing the extensible, scalable, resilient, and secure platform that we want, and providing a really good product to our customers so that they can trust us. So hopefully all of you can trust us. So yeah, we started off in the early days with a really basic product. We didn't even have debit cards to start with. And then slowly from that point, we've kind of iterated and added more and more features. So we've added pots so that you can organize your money, you can pay directly out of them, you can save money through those, and you can pick how to do that in the app. Or you can have your salary paid a day early. So we do that. You'll get a prompt in the app if you're eligible. And then you can sort that into the pots so that you can segregate all of your money for bills just straight away. You just never see it. Your bill money goes over here. You pay your bills straight away. And all of these are provided by an API. So this part is relatively straightforward. We have many product features We have many aspects of our API that we need to build. And then I think the point that things maybe are less clear are where things get a bit more complicated. So we have many product features, but those aren't the only things that Monzo has to build. For example, we have to connect to lots and lots of different payment systems. So these are some of the ones in the UK. And they range from MasterCard. We both are a card processor. We process all of our own transactions. But we're also a card issuer, so we issue our own cards. There's lots of different systems that go into that. That's relatively complicated. And adding those kind of things as separate systems allows us to keep those things simpler. Some of those things we've in-housed. So we used to have an external card processor, and now we've brought that inside. So we have a MasterCard processor written in Go. We had to add a load of ebcdic code pages to the Go programming language. If anyone knows what ebcdic is, it's the whole interesting different type of thing. And by doing that in one section of our infrastructure, we can isolate that complexity, and everything else doesn't have to be aware of it. So many of these things we've in-housed. MasterCard, one of them. Faster payments, more recently. We now have our own direct connection to faster payments. That is built on our own infrastructure. We built our own gateway, and that's now in-house. So all of those things we're doing because we want to build more resilient systems. We want to have more control over the product experience, but we also want to be able to own our own availability. And some of the other examples, for example, are chat systems. So when you chat to someone through Monzo, 24 hours a day, every day of the year, that goes through our own systems now. So we've in-housed that as a critical function of the business. And behind that, there's a whole team of people who will kind of chat to you and help you with your problems. So we both have APIs that do this in the app, but we also have bespoke systems behind that, which are what our internal teams use to like talk to people, manage a variety of tasks, that kind of thing. Over 50% of our staff use this on a daily basis. One of our colleagues, Sophie, gave a really interesting talk, support at the speed of thought. So it's a really good insight into how we build those internal-facing products. But again, like the examples we're giving here are that the problem space is quite large. And it gets even larger because we integrate with loads of other companies. So we integrate with IFTTT, so you can get real-time notifications of your payments. Flux, so you get receipts in the app. And all of these things, again, are increasing the scope of the domain and the number of systems that we're having to build. And then behind that, there's all the stuff that you don't see. So things like detecting and preventing financial crime, security. All of these things, again, are systems that we build in a kind of consistent way on our platform, but they're not things that are visible, really, to the outside world. So over time, clearly these things the number of things that we're working on as a company has increased. And that means the number of systems that we built has increased. And over time, that's meant that the number of services that we have has increased quite dramatically. So currently we have 1,600 services in production. All of them are very small. We use a bounded context, so they're very tightly scoped on the thing that they do. That allows us to be flexible because different groups can operate a small section of this code base. And as our organization grows and we have more teams, they can specialize in progressively smaller areas. And these systems are responsible for everything that powers our bank. So from payment networks, moving money, maintaining a ledger, fighting fraud, financial crime, and providing world-class customer support. All of these things are systems that we built as services within our infrastructure. So yeah, that's kind of how we get from essentially what started as a relatively simple product through to a system that now, at first glance, looks really complicated. In this particular diagram, we have color-coded areas based on teams that own and maintain these systems. So you can see there are like clusters owned by different teams within the company. This is clearly not a great way to like look at data, right? And this isn't an internal tool we use on a daily basis, but it kind of shows that there are many of these services and they are interlinked, and the way that we interlink those things is the kind of interesting part.
So you want to add a microservice. Where do you get started? So you start with a blank canvas. And this is the surface area that engineers are typically exposed to. They put their business logic in a well-defined box, and the surrounding portion makes sure that it works and is production ready, and provides all the necessary interfaces and integrations with the rest of our infrastructure. One of our biggest decisions as an organization was our approach to writing microservices for all of our business functions. Each of these units or each of these microservices of business logic are built on a shared core. Our goal is to reduce variance as much as we can of each additional microservice we add. If a microservice gets really popular, we can scale it independently. Engineers are not rewriting core abstractions like marshalling of data or HTTP servers or integration with metric systems for every new service that they add. They can rely on a well-defined and well-tested and well-supported set of libraries and tooling and infrastructure that we provide. When we make an improvement or fix a bug in the shared library layer, every service can benefit, usually without needing a single line of code change within the business logic. Here's an example where we made some improvements to reduce the amount of CPU time of unmarshalling data between Cassandra, our primary data store, and Go, which is what we use to write all of our microservices. Some of our services saw a significant CPU and latency drop. This kind of work has cascading and global improvements across the platform. It's like a free speed improvement for anyone who's working on business logic, and everyone loves a free speed improvement. So how can we compose services together to form a cohesive product or offering or service? We take a problem and subdivide it into a set of bounded contexts. The whole premise behind this is the single responsibility principle. Take one thing, do it correctly, and do it well. Each service provides a well-defined interface, ideally with safe operations. Consider that if you were going to expose this interface publicly to the public world, what tunable parameters would you want to expose to the world? You don't want to provide every particular knob, because that means that you might have lots of different permutations that you need to support. So as a particular example, here's a diagram of all the services that get involved when you tap your Monzo card at a payment terminal. Quite a few distinct components are involved in real time when you make a transaction to contribute to the decision on whether a payment should be accepted or rejected or something in between. And all of this needs to work as one cohesive unit to provide that decision. Part of that is calling key services like our account service, which deals with the abstraction of accounts all across Monzo. So it's not just providing bank accounts, but accounts as a whole, as a singular abstraction at Monzo. And also the ledger service, which is responsible for tracking all money movements, no matter in what currency or what kind of environment. It's a singular entity that's responsible for tracking all money movements all across Monzo. Now, this diagram is actually the maximal set of services, but in reality, not every service gets involved in every invocation on every transaction. Many of these are there to support the complexity of receiving payments, for example. There is different validation and work we need to do to support chip and PIN versus contactless, versus if you swipe your card if you're in the US, or occasionally if you're in the UK and the card terminal is broken. A service will only get called if it needs to get involved with a particular type of transaction. But this sort of thing is still really, really complex because accepted payments is really, really complex. Why do we have such granularity? We want to break down the complexity and minimize the risk of change. For example, if we want to change the way contactless payments work, we're not affecting the chip and PIN system or the magstripe system, so we can fall back to those if we get it wrong. So in September 2019, an EU legislation called Strong Customer Authentication came into effect, which is intended to enhance the security of payments and reduce the amount of fraud. The regulation focused on adding essentially a two-factor authentication layer when making payments. For a payment to succeed, a customer needed 2 out of the 3 elements. We had to make changes in our payments flow in order to be compliant, just like most other banks. So we had the option of baking in the strong customer authentication logic into the existing services that we had that were a part of accepting and making a decision on payments. But we chose to add additional services with a strict API boundary for validation. That means when the legislation inevitably changes and a new law comes into effect, or we want to iterate on our implementation of this particular legislation, we can only be concerned with that layer rather than tightly coupling the logic into our existing payments flow. It also means that other services, which are not completely payments related, like our customer support services, can call into the strong customer authentication set of services to get information about the specific state that a customer might be in. So if a customer writes in and they're getting all of their transactions rejected, then they can write in, and our customer service can essentially help by seeing the information about the state of the customer through these services. So strong customer authentication is a great example of a feature that had a lot of cross-collaboration between engineers working on payments, product, financial crime, and security at Monzo. Different parts of the project were independently implemented and deployed by engineers in the various teams. Each team was able to act locally on their specific components that they were allocated, but think globally to deliver the overall project. By having these API boundaries, each team was focused on their specific mental model, and essentially this caused a natural breaking down of a complex problem of implementing this large amount of legislation with a lot of moving parts into a set of simpler, composable microservices.
So when we're building systems like this, we talked about how we can either add systems or how we can change systems. And the way that we generally think about this is when we're building a system, we want it to be extensible rather than flexible. And that's like a subtle distinction, but rather than building a highly abstract service that can foresee like the many different ways we may need to approach a problem, we try not to do that. We try and add it in a relatively simple way and only abstract those things once we've actually done the thing a few times and we know that that abstraction is correct. There's been a couple of talks about at QCon about the costs of abstraction and premature abstraction. And I think this is like a very specific point. We can try and guess what our future requirements might be, but most of the times we've done that at Monzo, we've been wrong. And every time we try and build a highly abstract system, it turns out that even if we're kind of in the right direction, it's still not quite bang on. So instead, we want to be able to add new services that do the job very, very well and just have those defined responsibilities, and be able to change other systems, like small changes, to allow them to use that functionality and be extended. So that's kind of the difference we see, where we want to usually add some functionality rather than changing something to be super abstract. But that's not always the case. If we have a particular responsibility, you can think about that providing an API that provides a service to someone else in the company or some other group of services or people. And sometimes the responsibility of that system either remains the same and we just haven't implemented certain things and those things logically sit within that boundary, or we change the responsibility and we kind of refactor these things over time. So in this particular example, we might have a service and that has quite a defined boundary. And if we add additional code to that, then we're going to effectively extend that boundary. So the surface area is now larger. Now, sometimes that's the right decision if we're still operating in the same area of responsibility. But obviously, this is now a larger application. It's now more complex. When an engineer is either moved onto a team or joins the company, they now need to read more code within that box to understand how the system works. And it also means that if we just added code directly to the system without thinking about the larger overall problem, we may not be thinking about how it was originally kind of implemented. So when we're doing this, we tend to have a few patterns. Either we add additional services and update callers to use these, or we'll add additional functionality to these and they kind of grow, or many times we'll remove code and split them out and into a larger set of smaller services. So I think this is the thing to bear in mind. Our infrastructure is very much an evolving process. There are many services that won't change for a long time. We have a system that generates IDs. We generate standardized format IDs. That has not changed in 3 or 4 years. We might add some functionality to that, but it's very stable. But there are other areas where we're still learning more as we grow. And like those core abstractions, clearly we've learned a lot more about banking in the last 5 years than we knew 5 years ago. So we need the ability to change those things over time and refactor them. So while we may refactor individual services, generally we're doing this kind of like, someone described this as gardening, I think, the other day. We're evolving that system over time as we learn more about it. Yeah, so we'll either potentially expand services, break them up into a smaller number. Often, Sam talked about some of the patterns for these kind of things with monolith decomposition. All of those patterns still apply. So if we're breaking functionality out, we may pull that into another service, and the original service may temporarily proxy through to that new service while we update the callers to switch over. It's a bit of a migration process. In many cases, well, in a few cases, we've found that we've artificially split something, and after we've used that for a bit, it didn't really make sense. So in that point, we can combine those things together. If you find that you're changing a couple of services together, and even if you can deploy them independently, which all of the services at Monzo can be, if you find you're kind of changing two things a lot of the time, then maybe that's a signal that those things were prematurely pulled apart. And many times we've completely retired or replaced systems. As an example, we used to have a prepaid card. We don't have a prepaid card anymore. So the way that we interacted with that kind of model of payments is actually very different to the way that our direct card processor interacts. So we built the new system, we've issued everybody new cards, and then at some point, once all those cards were out of rotation, then we could shut those systems down and retire quite a lot of them. And I think that like iterative process is the thing that generally we take to heart at Monzo, really, both on an infrastructure perspective, but also from a product perspective. So a particular cartoon we love from Henrik Nyberg's is about we're trying to iteratively build a better product. Now, even right back at the beginning, if we tried to build a bank in isolation and not had like enough customer feedback, then we might have ended up with something that didn't really satisfy our customers' needs. And so by talking to people continuously and by making small changes, but making them quite frequently, we can hopefully make sure we're going in the right direction. And that applies both for our individual services and also for our product.
So there's been a few instrumental components that have allowed this ecosystem to flourish at Monzo. So we've talked about how we compose microservices and how we develop a set of robust libraries. But the other key layer is our core platform. The team that we work on focuses on providing components like Kubernetes and Cassandra so that we can host and deploy and develop containers, Cassandra for data storage, etcd for distributed locking, and components like Prometheus for instrumentation. We provide these components as services so that engineers can focus on building a bank rather than having lots of different teams doing individual operational work with many different components. Even with these components that we've specified, we provide well-defined interfaces and abstractions rather than surfacing the full implementation details about each of these components. So one key superpower we've been able to leverage is reducing the barrier of deployments. Engineers can ship to production from their very first week. Just today, by right about now, we would have had hundreds of deployments of various services all across Monzo. Once code goes through automatic validation and gets peer-reviewed and is approved and merged into the mainline, it's ready to be deployed to production. We've built a bespoke deployment tool called Shipper, which handles all of the complexities like rolling deployments in Kubernetes and running migrations in Cassandra. It deals with services that might look unhappy so that it can roll them back and deployments going bad. All this means is that we can build and roll out changes in minutes using a single command. Every engineer is empowered to do this at Monzo. Engineers shouldn't be expected to know complex things like Kubernetes and Cassandra. They don't have to write YAML or write CQL commands which are like hand-drawn to deploy their services. Code generation is another avenue where we optimize for engineer productivity, and it gives us a lot of standardization. As you can imagine, with now 1,600 microservices, the number of endpoints that are exposed is really, really big. We define our API semantics in protocol buffers format, and then use code generation tools with our own extensions. So we've extended upon the existing tooling available to generate the majority of boilerplate code. You can achieve something like this with gRPC. What this means is that each service is usually about 500 to 1,000 lines of actual business logic. And this includes, if you work with Go, or the if does not equal nil code as well. That kind of size is really understandable for a group of engineers. Even really simple things and core things like standardizing service naming. So, nobody is deploying a service with with innuendo names. Each service is well described in its naming. And service structure, the way we structure files, where do you put particular files within your code, is all standardized. The vast majority of services use a standardized service generator. So all of this code is generated up front, and the service structure is generated up front. No matter what team I go into, I know where I can find the database code. It will be in the DAO folder. Or I know where I can find the routing logic. It will be in the handler folder. Queue consumers will be in the consumer folder. This allows for much easier collaboration and onboarding for engineers onto different teams. At Monzo, engineers move around teams really often. We are really flexible and growing organization. So having this sort of standardization across all the teams is really, really important. Once you get used to the structure in one area, you can be a power user across the entire repository, across all of our services. Now, if you're working in a language like Go, you can build parsers and understand your existing code and extract information from code. Go provides this to you right from the standard library. As we've standardized our service structure, we've been able to build tooling and can operate across all of our services. For example, this tool on screen called Service Query, which can print out all of the API endpoints for a given service and parameters straight from the code. So even if it's not been well defined in the protocol buffers, which is definitely an anti-pattern, it can extract that information directly from the code. We can use the same tooling to do static analysis and validation when you submit a pull request. So that means a cognitive overhead for an engineer to peer review and make sure that this change is safe and potentially backwards and forwards compatible is all delegated to automated tooling. We've reduced the risk of engineers making breaking changes when they are deploying their code. And violations are automatically detected and can be rectified during the pull request process using automated tooling before they're merged into the mainline. Every single Go service using our libraries gets a wealth of metrics built for free. Engineers can go to a common, fully templated dashboard, type in their service name, and within the first minute of deploying a new service, have up-to-date visualizations and metrics about how many HTTP calls they're making, how many Cassandra calls they might be making, how many locks they are taking, CPU information, a wealth of information. This also feeds into automated alerting. So if a team has deployed a service and has not quite figured out the correct thresholds, they can they can fall back on automated alerting, which we already have. So that if a service is really degrading and causing potential impact, the automated alerting will catch that beforehand. Alerts are automatically routed to the right team which owns the service. So when a service is first built, before it's even merged into the mainline, each service has to have a team owner assigned to it. And this is categorized specifically in a code owners file, which is monitored and automated by GitHub. This means that we have good visibility and ownership across our entire set of services. Similarly, we've spent a lot of time on our backend to unify our RPC layer. So when a service calls another service to communicate with each other, this means that things like trace IDs and context parameters are passed across service boundaries. From there, we can use technologies like open tracing and open telemetry and open source tools like Jaeger to provide rich traces of each hop. Here, you can narrow down how long each hop took and the dependencies on external services and systems. We've baked in Cassandra integration and etcd integration right into the library so that we can visualize all of that in Jaeger. So it's not just about RPCs. You also want to trace your queries to the database. What actual query was made? How long did it take? Sometimes engineers want to follow a request path through service boundaries and see logs in a unified view. By having consistent trace IDs which are propagated, we can tag logs automatically on our backend, which makes it really easy for querying what happened between service boundaries, and you can log information and see in detail what every single request went through. Now, there is nothing unique about our platform which makes this exclusive to Monzo. We leverage the same open source tools like Prometheus, like Grafana, like the Elastic Stack, and OpenTelemetry to collect, aggregate, and visualize this sort of data. You can do the same on your platform.
So all of this philosophy is around having effectively a paved road where it's just the easiest option. And if you go along with that and the tools that we provided satisfy the problem that you have, you just get all of this stuff for free. So if that thing is so compelling that there's just like, there are other options, but you have to do a lot of other work, then it means you end up with this very consistent view across most of your platform. It's not mandatory. There are certain cases where we need to use other tools, but because we have a very, very strong default, it means that 99% of our system uses this default. And this starts from day one as an engineer. We go through the onboarding flow, and we kind of talk about the things that we want people to think about, and have a documented way to like bring people up to speed. I think having that, that training and giving people an easy path to onboard is really important. And then you can rely on shared expertise across the company. So we have lots of patterns for solving problems across all these services and within many teams. And as engineers join the company, as we grow, we can leverage that repeatedly. But crucially, you don't need to know how 1,600 different systems work. Different teams are working on a cluster, and those clusters operate very particular systems. So generally, a person will join a team, and they'll be looking at a very particular thing. And that applies to lots of different things. Local development, for example. Right now, it's clearly impossible to spin 1,600 things up on your laptop. Dockers, containers with your database in don't really like that many things connecting to you. But building Go binaries is really quick. So you very rarely need to run many of these things. You're running a subset, and we have essentially an RPC filter that can detect that you're trying to send a request to a downstream that isn't currently running, and it can compile it and start it, and then send the request to it. And that means that as you're using the platform locally, you just spin up the things that you're needing. And we'll refine that progressively over time. So yeah, there are some times where we do need to deviate from this paved road. For example, we use machine learning systems that are primarily in Python. But for most of our business logic, our approach in Go satisfies those requirements. And that's really the benefit of the microservice architecture. We can use the right tool for the job. In our case, Go is generally that right tool. But when we do need something else, we can totally use that.
So in summary, we accept that we've traded off some computational efficiency. But as a result, we've been able to leverage organizational flexibility by building services which are granular enough to be easily understood. Ownership is really well-defined, but it must be well-defined, but can be more fluid as a response to market behavior and goals of the company. Each service shares the same code structure and the same tooling. This reduces cognitive overhead for every engineer that is currently at Monzo and joins Monzo. It has allowed us to gain a lot of scalability by being able to independently deploy these microservices.
And by standardizing on that small set of technology choices, we can, as a group, collectively improve those tools. So engineers can focus on the business problem at hand, and our overall underlying systems get progressively better over time. And yeah, that means we can focus on the business problem. We don't have to think about the underlying infrastructure all the time. At the same time, our platform teams can continuously work on that and raise that bar of abstraction continuously, so that as we go, things get easier and easier.
So breaking down the complexity into bite-sized chunks means that each service is simpler and easy to understand. The granularity and ownership of services reduces the contention between teams, while risk is reduced as we can make small, isolated changes to specific sections of our systems. All of this is in aid of reducing the barriers to make changes. Allows us to serve our customers better, which is ultimately what we want to do as an organization. We want engineers to feel empowered to work on new and innovative functionality and deliver a better product to customers. Cool. Thank you very much.
Thank you very much. We do have time for questions, and I'm sure we'll have a few. Oh, here we go. I'm going to start at the front because it's easy.
Good.
Hi, thanks so much. I just wondered about, do you have strict guidelines on things like the maximum size of a service? And do you have strict coding guidelines as well, length of maximum number of lines of code and a method and things like that?
We don't prescribe any strict guidelines because there will always be exceptions to any sort of guidelines that you put in. In terms of like code formatting and stuff like that, Go is really, really good at enforcing that sort of stuff. So making sure that you have proper error handling, make sure that you're not skipping over errors, which is something that Go allows you to do. We have static analysis as an advanced check on top of that to make sure that you are not papering over errors, even if you have to make a really strong justification and add an explicit annotation, a comment in the code to explain why an error is being skipped, why you think this will succeed 100% of the time, even though the interface doesn't allude to that. We don't prescribe any strict guidelines in terms of the amount of code you can have within a function. Ultimately, code needs to be readable to other humans. Computers are really good at optimizing code and squishing it down and like inlining it when necessary. So optimize code for readability for humans. So one of our engineering principles is not to optimize unless it's a bottleneck. And that sort of stuff works really, really well.
And we also have on our engineering principles, which is something which we kind of expect everybody to adhere to. We want to optimize for code being read and for code being debugged. So yeah, optimizing introduces complexity, like every time. And it's pretty rare that we actually need that complexity. So optimizing for legibility, if that's the size of functions or whatever, yeah, it's the best way.
Do you ever find that you need to update a whole bunch of services at once? And how do you go about doing that? So for like a security vulnerability or something like that? Yeah,
good question. I can't think of many times we've had to do it for security reasons, but yeah, I can give you a very concrete example. We have an interface to send metrics it goes to a Prometheus library, but it's kind of wrapped. We used to use InfluxDB, and we subbed that out for Prometheus without any code changes because we had this like very simple interface. But that interface does not have a context, and we want to be able to propagate contexts all the way through our stack. So at this point, we have 1,500 services, which have many, many, many instrumentation calls, and we need to add a context parameter at the beginning of every single one because we want to update the shared library. I think this is where having a monorepo works really, really well for us. In that particular case, we wanted to change the library to change the interface. So if we couldn't refactor everything in one go, we would have had to add a new one, mark the old one as deprecated, have some migration period, and then like some enforcement mechanism to get people to move over to the new thing. Because we have a monorepo, we could change that and use Go's reformatting tools to add a context to every single call across the entire code base in a single commit. And then, yeah, that was a pull request. We had to get approval from the teams because we'd changed their code. But that meant that we could do that refactoring like in essentially one atomic unit. Now we have to deploy 1,500 services. So we have tools around that. But again, like we have lots of testing around these things, and we have lots of tooling that allows us to initiate a rollout, and if that's not working well, it will automatically roll back. So like, because we have those safety mechanisms in place, we can do that with a quite high degree of confidence.
So you're using Cassandra as your main database, which I'm sure surprises some because it's not generally associated with like ACID and all of these other things that you kind of expect of banks, but it does have tunable consistency. Could you comment on how you use it a little bit?
Yes. So I think there's a common misconception that banks must be ACID compliant. Eric Brewer wrote a really interesting post, I think in like 2006, several years ago, about how banks are basically available with soft state and eventual consistency. So they're base rather than acid, which if you do chemistry is a super entertaining joke. And I think that's the thing that we really have to like think about here. In our case, we use Cassandra because it provides a masterless, horizontally scalable database that gives us a lot of controls over writing the data to multiple locations. We don't have this like one server, a primary that fails over to a secondary, and we can avoid those problems. But we've traded off the ability to have transactional consistency. So that might sound insane for a bank. But we can provide those things. And in many cases, the financial networks already deal with this. If you tap your card, which supports offline transactions in a store, most cards will allow you to do 3 or so transactions for up to £30. And hypothetically, your bank may only find out about that 2 or 3 days later, at which point the bank is now told you spent £28 on your card. If you don't have £28, they're still going to remove £28 from your account. So you have a series of like commutative operations that are like debit £28, credit lots of pounds, debit some number of pounds. So when we talk about consistency and transactional isolation, you're trading off financial risk for consistency. And sometimes that's okay, and sometimes that's not okay. And we have a variety of different systems. Some things we won't allow transactions to happen unless we can achieve a lock and successfully complete a transaction and then unlock. But in many other cases, we get told about it 2 or 3 days later, in which case we don't need a lock. We have a queue of things to apply to people's accounts. And at that point, like we don't really rely on the eventual consistency that much in that particular case, but we don't need like transactional isolation.
Considering the volume of microservices, how do you maintain versioning and integration testing and system integration testing?
So for versioning and integration testing, I think this is where our like mono repository, our single repository for all of our services, really, really helps. So for example, every single service that is deployed runs through a battery of unit tests, but we can do automatic validation and inference to see, go through the AST and figure out what services have changed. So we only need to run the tests for services and their dependencies and their upstream dependencies. So the service graph can get smaller and smaller. So if you've made a localized change to your particular service, we can isolate the testing to that service. Obviously, we also have full integration testing on like offline boxes that we run periodically to make sure that the full state of the system is in a consistent and like a nice green state. Sorry, what was the last bit of your question? System integration testing. So naturally, what we do is for our integration testing, we spin up these real components in containers, and we're doing a bunch of work at the moment so that these systems can call into our platform. So we do run integration testing into our staging platform. Ideally, we'd be able to run these integration tests in a isolated platform, like maybe in production, maybe some variation of production, which is not a testing environment with test data, to make sure that we are like testing our assumptions properly. We now have 4 million customers. It's a completely different order of magnitude than having a few thousand test cases in a staging environment. So to make sure that we are testing our assumptions properly. So that's a unit of work that we are undertaking right now.
And we've got time for 2 more questions. There's one over there and one over here.
Cool. Just a quick question. In terms of testing microservices, in terms of environments, you kind of get your test pre-prod, prod. I'm more interested in terms of the data side and how you test, I guess, around that and manage, considering GDPR, considering you're working with a lot of customer data. Like, how do you kind of manage, or what guidelines do you have or tips in terms of just, I guess, testing lower database environments, if that makes sense?
So in the case of testing in staging or pre-production, we effectively we want to create test cases that are realistic, but they don't need to be real people. So we have lots of like things that generate people's names and like randomized data, but then have relatively realistic test cases that we can generate, pre-fill into the database, and then we can test with those. So there's kind of that aspect. As far as soon as you're in production, I mean, yes, you have real people's data, and that is something that we take very, very seriously. So we can't just run tests against people's accounts. We do use, so one thing that we did when we ran crowdfunding a year and a half ago, we ran that through the same platform, which again might sound a bit crazy. So in order to know that you can support that, you need to be able to test things very, very accurately. And one of the techniques we used there was using shadow traffic. So I think Facebook and a couple of other companies have tried this. Essentially, we updated our system to take a request that was an idempotent, let's say a read, and we could pass that through and then give the response back to the customer. And then this proxy could then sit there and repeat that request a randomized number of times. Yeah.
Hi there.
I think we're being asked to stop.
Okay. No? No? That's a no. Sorry, everyone. Suhail and Matt will be around for a little bit if you want to try and grab them.
Cool. Thank you very much.
Thank you.